All right, now let's move ahead with the Pascal's law. So here Pascal's law states that the pressure in equilibrium is same everywhere. This is the most important part. If the gravity is neglected, that means I'm going to consider G is equal to 0. So pressure is equal to H rho G. If I substitute here G as 0, then the pressure would turn out to be 0. But this is inclusive, this is exclusively of the fact that we are not considering the atmospheric pressure. Now look at the diagram. What I mean to say is the top surface of the liquid, let me call this point as point A. Over here already the pressure is PO, that is the atmospheric pressure. Now suppose if I dive in to the water at say point B, which is at H depth below the surface, then over here the pressure PB should be ideally equal to H rho G plus PO, because the pressure is the sum of the total pressure of the liquid column above it and the air pressure. So if we neglect the gravity, then at PB the pressure is P naught. In the same way, if I take point C over here, which is at a depth even more larger, let me call this as H1, then pressure at point C will be equal to H1 rho G plus P naught. But since we have taken the gravity as 0, so answer is again P naught. So in absence of gravity, the pressure is P naught everywhere. Now, how do we support this one? Let's say this. So here we have a rod which is in equilibrium, right? So I'm going to rub off all these stuffs, and we are being given a rod in equilibrium. Equilibrium means it is stationary inside the liquid. I'm going to consider the liquid to be water, right? Now, since this rod is stationary, from all sides the forces must be equal and opposite. That's why the net force on the system would be 0, right? Okay, now let me consider two areas. One is this area. Let me call this area as A and this area as B. By the way, the area magnitudes are the same because the cylinder is having same cross-sectional area everywhere, right? The regular cylinder. And now both the surface area will be experiencing a thrust due to water. So thrust is always, now if you look at this particular area, so the force or the thrust is always perpendicular to the area. So thrust by the water will try to compress it in this way, but the thrust from the bottom part like this area is B area, and the thrust would be like this, because the thrust would try to compress the cylinder from all sides. Since the cylinder is in equilibrium, the net force has to be 0, which means F2 and F1 should be equal. Then and only then the cylinder can be in equilibrium, right? Okay, so what am I going to do is I'm going to simply say F1 and F2 are equal because the cylinder is at rest. So F1 is equal to F2, and rest all other forces are equal and opposite, so they are going to cancel it off. Multiplying both sides by the area, so F1 times A is equal to F2 times A. So this is pressure is equal to pressure. Let me call this as pressure at point 1, pressure at point 2, or pressure at point A and pressure at point B. Let's take it that way. So this is how we can prove it. Now there is another version of the Pascal's law. It states that in an enclosed fluid, if the pressure is increased in any part of the liquid, then it is transmitted equally to all parts of the liquid. Now over here we have a setup like this, and there are many pipes which are coming out from different areas of this setup, right? So this is a three-dimensional setup. You may consider this as a sphere in which there is already water, and from few areas we are pulling out the pipe, and then there is one small area or on the top from where we can apply the force which can create the pressure in the liquid, right? So now suppose the pressure applied over here, you can very well see before applying the pressure the liquid is at a common level, right? So everywhere the pressure is same as per the Pascal's law. That's why the liquid is at one particular height, and if the liquid is higher at one area and lower in another area, that will create a pressure difference. The fluid will start flowing. So when the fluids are at rest, they will be at common level, right? Because they are at rest, so the pressure everywhere should be the same, right? That's why the liquid is at common level. Now you apply some force. Let me call force as 10 Newton, and the area of this piston is, say for example, 1 meter square. So the pressure that you are creating is equal to force upon area, that is equal to, and that is F perpendicular, right? So that is 10 Newton divided by 1 meter square. So the answer is 10 pascals. Now the 10 pascals is going to be transmitted everywhere. So the 10 pascals pressure would be transmitted over here, 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 in all the open ends of the pipe which are connected to the spherical container. Everywhere the pressure is going to be transmitted, and that is because of the fact that this piston will move downwards, right? Let me draw this, the new location of the piston. Now the piston is located here. The piston comes down, so the liquid has to go out somewhere, because the liquids are incompressible, right? So what is going to happen is some volume of the liquid is going to decrease from the top, and that volume has to increase everywhere in the other parts. So the 10 pascals liquid is going to push the liquid everywhere, and due to which this free surface of the water in all the pipe is going to reduce by the same amount. Now you will see that the liquids will rise to a new height. And when we do this experiment, we find that the final height of the liquid is same everywhere. Correct. So the height increase is same in all the pipes, whether they are coming out from the bottom or whether they are coming from the top or the middle part, irrespective of that, which indirectly proves that the final pressure is same everywhere. That is result of the equal transmitted pressure. So that is what it means. Okay, now here is the Pascal's law in my own version. So this is a container, right, having two pistons. Now I'm going to consider one piston like this, having area A1, and over here another piston having larger cross-sectional area A2. This area is A2. By the way, this is a cylindrical shaped vessel, right? So please excuse me by the drawing part, right? So now this is an upright vessel. This is standing and this is ground, right? So this part is the ground, this is the ground. So you can very well see that the piston, let me call this as piston P2 and piston P1. Now piston P2 is at some height above the ground, say h height above the ground, and P1 piston is on the ground, direct in contact with the ground, right? I'm giving you 3 points. Let me call this point as A, this point as B, and this point as C. Now look at these 3 points. And yeah, I forgot to mention one thing, that this is entirely filled with water, or you may consider oil. This is filled with oil, and liquids are incompressible. So this entire this setup is filled with the liquid oil. Okay, now we are supposed to press or apply force F1 from piston P1, and you will see that the piston P2 will rise up with force F2. But my point is that before applying the pressure, P1 was here and P2 was here. Piston P1 and P2 are intact at their own positions, right? Now I'm saying when the fluid is at rest inside the particular this container, what do you think? Where is the pressure higher, at A, B, or C? The correct answer is C, because look at this point. A is at less depth, or HA, B is at HB depth, and C is at a depth of HC, right? So look at this one. The depth of C is highest with respect to top surface of the liquid. So pressure at C is greater than pressure at B is greater than pressure at A. Correct? The liquid was in equilibrium. All right. Pressure at C is larger. Pressure at B is less, and the pressure at A is least because of H rho g. I am considering gravity over here. Now you may ask me the question that, sir, why doesn't the liquid flow from higher pressure to low pressure? Because the gravity. You may consider a small section of the fluid. I'm using a black color portion of the fluid. Now just imagine this over here, the pressure is PB, and over the top over here the pressure is PA, which is less. So the fluid must go up from high pressure to low pressure. But the weight of this entire part, mg, is balancing the upward difference in the pressure thrust. So the high pressure to low pressure thrust wants to push this liquid up, but the weight is pulling down. So that's why this particular part is in equilibrium, right? So I'm just removing this part. All right, and I have given you an idea that which over where the pressure is going to be larger, right? And as I said, that pressure at C is going to be the highest and pressure at A is going to be the least. And why doesn't the liquid go up from high pressure to low pressure? Because of the gravity. Everything is in equilibrium, right? Now my question is, let me give this force of 10 Newton over here, and let me call this area as 1 meter square. Okay, now, so the pressure generated at the bottom where I'm applying the force on a smaller piston is how much? So the pressure generated is equal to F1 upon A1. So 10 Newton force divided by the area is 1 meter square. So the extra pressure generated in the liquid is 10 pascals. Okay. Now what happens is, at point C the pressure was PC. At point B the pressure was PB. And at point A the pressure was PA. So PA, PB and PC were the pressures before applying the force on the piston. But now, since you have exerted the force, due to which the pressure everywhere becomes more by an amount of 10 pascals. So here pressure becomes PC plus 10 pascals. Here the pressure was PB, and over here the extra pressure becomes 10 pascals. And over here the pressure earlier was PA, now the pressure becomes PA plus 10 pascals. I don't mean to say that everywhere the pressure becomes 10 pascal. No, that's wrong. Everywhere the pressure increases by 10 pascals is what is the meaning of Pascal's law. Most of the students are confused over here. Now just imagine what is going to happen. Since the fluids were incompressible, this piston, right? This piston goes inside. So liquids are incompressible. So this piston has to go up. Now, which pressure is responsible to push this particular piston upwards? It is not PA or PB plus PC. It is only that extra pressure that of 10 pascals that you have created. So that's why the pressure increases by an amount of 10 pascals everywhere. I don't mean to say that the pressure becomes equal 10 pascals everywhere. No, that's wrong. Already there were difference in the pressures in the throughout the liquid, but the pressure increases by 10 pascals everywhere is the meaning of Pascal's law. The applications of the Pascal's law, right? So first is this hydraulic brake. So what do we do is, when we apply the force on the brake pedal inwards, so what happens is this piston over here, right? This piston goes in. So this piston goes in, so the oil which is present over here goes down, and as a result, so the oil is like pushed like this and the oil goes down. Some oil goes on the other side. The similar setup is also located in the other areas because there are 4 tires in a car. So these 4 setups you will see everywhere, right? Now some amount of oil goes down. As a result, these pistons P1 and P2 are pushed outwards. So this semicircular shoe presses against the brake shoe. Correct. And since there is a pressing, this spring would be pulled outwards and there is a braking applied and the car stops. Now, what will happen if you remove your foot from the pedal? Let's see that, right? So now the moment you release your foot from this pedal, so the spring will again pull these 2 semicircular brake shoes in, these brake pads in. As a result, the P1 and P2 piston will be pushed inwards. So the oil volume here will decrease. So the oil will be again pushed upwards like this. And again, the oil will be filled in this master cylinder, which will push this particular piston outwards. and this again brake pad will come at its original place. So this is how it works. Now this is a hydraulic press, or you may call this as an hydraulic lift as well. This is basically lift. If you keep some hard, say for example, piston over here, then this load will be pressed, and that would be known as hydraulic press, right? So both moreover the same. Now what happens is, this is a smaller area, right? So what we are going to do is, we are going to apply the external force on a smaller cylinder. Please be aware, on a smaller piston cylinder we are going to apply the force. So let me say that 10 Newton force is applied on an area 1 meter square, and this area A2 is very large. Over there the load is to be pressed, which is to be lift, right? Which is to be lifted. So suppose this area is 1000 meters square. Now what does Pascal's law states? That the pressure generated over here, that is F1 upon A1, that will be equal to 10 Newton upon 1 meter square. So the 10 pascals is what is going to be created over here. Now this 10 pascals of the pressure, that will be pushing this particular area or the piston upwards. So which is responsible for pushing this particular piston upwards? It is 10 pascals of the extra generated pressure. So here the pressure is 10 pascals. Let me call this as P. So the force is F2, which is in the upward direction, that is pressure times A2. So here 10 pascals times 1000 meters square. So the force generated is 10,000 Newton. Due to this tremendous upward generated force, this heavier load can be lifted. That is what is the meaning.